Hi there, welcome to my channel Mando to Fundo. In this video, I am going to discuss about the solution for validating the binary search tree. Let's look at the problem description. We are given a root of binary tree and we have to determine whether it is a valid binary search tree. So the valid binary search tree is the left subtree of a node contains only nodes with the keys less than the node's key. The right subtree contains the value greater than the node's key. Both the left and right subtree must also be a binary search trees. So let's take this example. So here the parent node is 2 and its left child is less than the parent node's value and the right child is greater than the parent node. So this tree is a valid binary search tree. And the second case, the parent node is 5 and the left child is 1, which is valid, and the right child is 4, which is not valid. This is supposed to be greater than 5. Let's take this example 2. The parent node is 5 and its left child is 1, which is less than 5, so that is valid. And the right child is 4. This is less than the parent node, which is violating the binary search tree property. So the entire tree is not a valid binary search tree. And the number of nodes in the tree is in the range from 1 to 10 to the power 4. And the node values possible range is minus 2 to the power 31 to 2 to the power 31 minus 1. We have the input array that represents this tree. So the basic idea is whenever we visit a node, we have to compare the possible valid upper and lower bound value for that node at that level. So initially at the root node, the possible values as per the problem constraints is 2 to the power minus 32 to 2 to the power minus 2 to the power 32. So that is the lower and upper limit for node in this level, root level. When it visits the left child, we have to adjust the upper and lower limit. So when it comes here, the upper limit for this node is changed to the value of its parent. So for this part of the tree, all the values should be less than 5. So the upper limit is 5. The lower limit is 2 to the power minus 32. So that's the idea. And then when we visit the right subtree, the lower limit is set to the parent node's value because all these nodes should be greater than 5. So this value will be set as a lower limit and the upper limit is 2 to the power 32. So as we go down, the upper limit and lower limits are adjusted based on the parent's node, the currently visited node's parent's node's value. So if that if the value of any node is beyond the valid range, then that tree is not a binary search tree. For example, here if we have for example here we have 4, but that is less than 5, but all the elements are supposed to be greater than 5 on this part of the tree, but here we have 4. This violates the binary search tree property, so we are returning false. Let's look at the flowchart. Input for this procedure is pointed to the root node and valid lower limit value and upper limit value for that node level. So to begin with, the lower limit is set to 2 to the power minus 32 and this one will be set to 2 to the power 32. So and then inside the procedure we initialize the left valid and the right valid variables to false initially, and first we check whether that root node is null. If so, we return that as a valid binary search tree. Otherwise, we check whether that node's value is within that limit, upper and lower limit. If it is not in that limit, that means it is violating the binary search tree property, so we are returning false. Otherwise, we go down to the next level. Meaning the current node's children's will be processed. So we make a recursive call to process the left subtree. So when we do this call, we pass the left child and then the lower limit, and the upper limit is the root node's value, because as I explained earlier, the left subtrees all the values should be less than the root dot val. So that's why we set this upper limit and then call it, and the return value is assigned to the left valid variable. Same way we call the right child. Same way we make a recursive call for the right child and we pass the lower limit value as the root node's value, the root node's value as the lower limit value, and the upper limit is the maximum possible value. The reason why we are doing this, all the elements on the right side should be greater than the right. So the root node's value is the lower limit. And we assign the return value to the right valid variable. And then we, if both the left valid and right valid is true, then this valid will be true and we return that. If any of them is false, then this valid BST will be false. And finally we return that back to the caller. Let's move on to coding. First I call the helper function from the isValidBST and pass the root node and then the minint as the lower limit and maxint as the upper limit for the root node's value. Next I write the helper function. So in that function I declare the left valid and right valid variables and initialize them to false. Then I check whether the root node is nil. If it is nil, then return true. Then I check the root node's value against the lower and upper limits. If it is within that limit, I will proceed. Otherwise, I return false because it violates the binary search tree property. So we return false. Then I call the isValid BST helper function to process the left child. In that I updated the upper limit value to the root node's value. Then I'll make another recursive call to process the right child. So in that case, I set the lower limit to the root value and the upper limit will be left as it is. So once these two functions returned, then I will check whether both are true. If so, I will return true, otherwise false will be returned back to the caller. Next, I am going to run the test cases. Okay, it's accepted. Next, I am going to submit this program. Cool, it's accepted. Next, I am going to do the code walkthrough with sample input. We have this input tree and the expected output is false. The reason is we have the right child which is smaller than the parent, which is violating the binary search tree property. So we have to return false. So let's see how this code returns false for this case. First, the isValid BST is called with the root node, which is 5, and then the math minint and math maxint as the lower and upper limit. So inside this function, we check whether root is null. No. So we are proceeding, and we are checking this root value is within these two upper and lower bound. That is true. It is within the valid bound. So we are proceeding further, and we call this valid BST helper to process the left child. So what we are doing is we pass the left child, and then we leave the lower limit as it is, but we update the upper limit to the root elements value, because all the elements in this left subtree is less than 5. So the upper limit is 5. So that's why we change this upper limit to 5 and make this call. And we come here, and it's both left and right childs are nil. So this condition is met when we call their child, left and right child, and eventually it returns true to the parent 5. So that's why this left valid is true here. Next, in from frame 0, the isValid BST helper is called for the right node. So when we call when the right node is passed, we have to set the lower limit with the value of the root node, because all the elements on the right subtree should be greater than the root node. So that's why we are updating the lower limit. Okay, so that call happens here, and here when we come here, we have the lower limit as 5, but this is less than the lower limit. So this condition is true, so we are returning false back to the parent. So that's why in frame 0 we get the right valid as false, and then we return left valid and the right value. So in that case we returning false eventually to the isValid BST caller, and we get the false as expected. Next I am going to do the time and space complexity for this solution. Okay, let's consider two cases for doing the time complexity analysis. The case 1 is where the given tree is not a binary search tree, and the case 2 is the given tree is a binary search tree. Okay, so for this case the number of nodes traversed to declare that this tree is not a binary search tree, we had to traverse 3 nodes. So first 5, 1, and then when we traverse this node, this violates the property, so we return without processing any other nodes. So that's why the number of nodes processed is 3. For the valid binary search tree case, we have to traverse the entire tree, all the nodes in that tree, in order to determine the tree is a valid binary search tree. So in that case we have to traverse all the n nodes in the tree. So that's why the time complexity for this algorithm is order of n. And the space complexity is we do not allocate any additional space with respect to the input size. We just use local variables. So but the space, this algorithm uses the stack space because we are doing the recursive calls. So at any point for this algorithm, the maximum number of active frames is log n base 2, which is the height of the tree. So for this case, maximum 2 frames is needed. So log n base 2. That is the space complexity for this algorithm. Thanks for watching this video. Have a great day.